Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. I realize it's almost 5 years that I've been doing these live streams. I started right at the beginning of the pandemic. Anyway, we'll have to note when 5 years have really gone by. Well, let's see. I have all kinds of questions that have come in here. Let's start off with one from Derek. How do we know how far stars, galaxies, etc. are away in space? Okay, good question. So the key thing is a piece of geometry. So the Earth goes around the sun in its orbit, and it has a certain distance that it goes in its orbit. And if you're looking at a star from the Earth from one time of the year to 6 months away in the year, the Earth has moved to the other side of the sun. And so if the star has stayed in the same place, then the angle that you see the star at in the sky has changed a bit. And so what you're measuring is the so-called parallax, the change in the angle at which the star appears, which means where it shows up on the sky when the Earth is on one side of the sun and on the other side of the sun. And so one common unit that's used to measure the distance to stars are things called parsecs, stand for parallax seconds. That's the number of seconds of arc that are changed in the angle when the Earth goes from one side of the sun to the other. What is a second of arc? So when you measure angles, you measure all the way around. A circle is 360 degrees. A right angle is sort of a corner. That's 90 degrees. And the way that angles get measured, usually it's in degrees, where 360 degrees is all the way around. Back in the time of the Babylonians, it was sort of thought that there were about 360 days in the year, and the angles were measured like measuring out days in the year. So 1 degree was like 1 day out of the year. So that meant that you could go on and you could say, well, if you want to measure a smaller angle, you could say, well, what's 1 minute out of the year? That's a smaller angle, an arc minute. And then even smaller is an arc second. And so there are about 30 million seconds in a year. So going all the way around a circle, there'd be about 30 million arc seconds. And so when the Earth goes from one side of the sun to the other, the angle of the star to a star doesn't change very much, but it changes by some number of arc seconds as the Earth goes from one side of the sun to the other. And that leads to this measurement of being able to say that when it's 1 arc second difference, that corresponds to the star being a certain distance away. And once you have that measure of distance, you can talk about the distance to stars in terms of parsecs. Slightly more common in the non-professional astronomy world is light years. So a light year is the distance that light goes in a year. So light goes about a foot in a billionth of a second. So in 1 nanosecond, light goes about a foot. That means in a second, light goes about 1 billion feet. And that's about 186,000 miles that it goes in a second. So then you can work out, for example, the distance to the sun from the Earth to the sun is about 93 million miles. And if light goes 186,000 miles per second, you can do the arithmetic. I can't immediately do that in my head. Well, I probably can do that more or less in my head. But in any case, the answer is it takes light about 8 minutes to get from the sun to the Earth. The nearest star other than the sun is Alpha Centauri. It takes light about 4 years to get from Alpha Centauri to us here on Earth. And so that means we say that the distance to Alpha Centauri is about 4 light years. It's also a parsec is, I think, 3.1 light years, if I remember correctly. So the distance to Alpha Centauri is 1 point something parsecs. So that's sort of the basic way that one measures distances to things like stars, is by that parallax, the difference of its angle when the Earth is on different sides of the sun. When you're getting to measure things much further away, it gets trickier, because the amount that the parallax distance, the amount that they'd move in the angle in the sky is incredibly tiny, and you wouldn't notice it. So when it comes to measuring like distant galaxies, there's a different way of figuring out how far away they are, and that's based on the idea of redshift. So the universe is expanding. The universe started at the Big Bang about 14 billion years ago as something probably essentially infinitely small, probably very different from the way the universe is today, very hot, possibly infinite dimensional rather than three-dimensional as it is today. But in any case, it started in that tiny state and has been expanding ever since. It kind of got this big push to expand. And actually, the only effect, it's been kind of free running since then, pretty much. And the only potential effect is that all the stuff in the universe might be pulling the universe back in by gravity and making it expand less quickly. But actually, what seems to be happening is that the universe is expanding right at the point where it just about goes to sort of a fixed expansion rate, where the force with which it was started expanding at the Big Bang and the force of the gravity trying to pull it back more or less compensates, so that it's eventually going to be sort of freely going out at a certain rate. It's a little bit tricky to say what that rate is, because in some sense it's sort of the speed of light, but it's a little bit tricky to describe what that means when you're talking about the whole universe. But in any case, so the universe is expanding, and and that means that if the universe is expanding, then things in it are also expanding, because they're filling up the universe. They're still filling up the universe. There's sort of a question of what expands and what doesn't. If absolutely everything in the universe expanded, from every atom to us to the Earth to our galaxy to whatever else, if everything expanded, we wouldn't even notice that things were expanding. So what actually happens is that things which are held together by forces of gravity or other kinds of forces, they don't expand, or at least very not to an significant extent. In a sense, what the expansion of the universe does is it produces this kind of overall tug on things that tries to pull them apart, even as they may be being pulled together by force of gravity or by other kinds of forces. And so, for example, our galaxy is sufficiently tightly held together by the force of gravity that it doesn't expand. If we look at the cluster of galaxies that we're in, it doesn't expand much either. If we look beyond that and we look at galaxies that are further away and are less gravitationally attracted to each other, then eventually the sort of force that is associated with the expansion of the universe will kind of take over, and the galaxies will be pulled apart. Okay, so what that they're being pulled apart? How can one figure out how far away they are? Well, there's two basic things one might do. One is to assume that one knows how bright a galaxy is, how much light is being produced by a galaxy, and then to say, well, if the galaxy is dimmer, it must be further away. That's a little bit fraught with difficulty, because a galaxy that's far away, the light from it might have started coming to us 5 billion years ago. And it could be that galaxies 5 billion years ago aren't quite the same as galaxies today. They could have had less light or more light that they produce. So the idea of saying we'll measure how far away it is by saying it's a fixed amount of light from a galaxy, and then the further away it is, the dimmer that will seem, might have difficulties. Why might the galaxies be different today than they were in the past? Well, what happens is that, for example, different chemical elements, like, I don't know, particularly the heavier elements going up to things like uranium and so on, they were not produced in significant amounts in the very early universe. Things like hydrogen and helium were produced in the very early universe. Very early universe, lots of hydrogen, about a quarter as much helium, and then you go down to the other elements, there'll be less and less and less of those other elements. The heavier elements are mostly produced by exploding stars, by supernovas, and the thing is that if there haven't been many supernovas yet, you won't have had many of those heavy elements produced. So the stars that sort of come later get the benefit of earlier supernovas and earlier kind of production of heavy elements, which can change how those stars work. And there are probably a bunch of other effects in kind of later stage galaxies working differently. For example, the central black holes in galaxies probably get bigger, and that has some effect, and so on. In any case, so first thing is just look at how bright the galaxy appears to us to be, assuming it's a fixed brightness. But another thing is, because the universe is expanding and faraway galaxies are getting further and further away from us, if you work out the geometry, you realize that if the universe is sort of constantly expanding, things that are further away are effectively receding from us, going away from us at higher speed than things that are close to us. And so the effective speed with which a thing far away is moving relative to us is higher than the effective speed the thing is moving if it's closer to us. Okay, so what does that mean? Well, there's this thing called the Doppler effect, which is sort of an everyday thing in the sense that you can experience it in an everyday fashion with sound. The thing we'll talk about in a moment is the Doppler effect with light, but with sound, here's how you notice it. If you hear something like a siren go past you, as it approaches you, it's a little bit higher pitched. As it goes past you, it flips to being lower pitched. Why does that happen? Well, the sound that you hear comes because there are vibrations in the air, and the vibrations in the air are coming at a certain, they're moving towards you at the speed of sound, and there are certain, the distance between the vibrations might be, I don't know, a centimeter or something, and you'll get the vibrations are coming, and they're coming at the speed of sound, and you're hearing them as the pieces of that pitch that is being made by the siren. If the thing is moving towards you, there'll be kind of the speed of sound, but then there'll also be the speed of the vehicle that's producing the siren, and those two speeds kind of add up. And so the rate at which those vibrations will arrive at you is larger because they're arriving because of the speed of sound, and they're arriving faster because the vehicle is, you're also getting the kind of speed of the vehicle moving those things towards you. So that means that the vibrations are effectively arriving at you more quickly, more rapidly spaced, and that's what leads to it sounding like a higher frequency as it's approaching you. As it goes away from you, the opposite happens. The sound is coming to you from it, but the sound is starting with something that is moving away from you, and so the speed with which the things arrive will be slower than it would otherwise be. And so that means that the pitch of the sound will be lower because the distance between those, because the time between the compression in the sound will be shorter, will be longer, I'm sorry. So in any case, the main effect is the thing's going away from you, the frequency is lower. Same thing happens with light. It's a bit trickier with light because with something, okay, tricky fact about light. In the case of sound, if something is moving and it is producing a sound wave, the sound wave effectively is moving at the speed of sound, let's say, plus the speed of the vehicle that produced it. In the case of light, one of the mysterious things that was discovered pretty much implicitly discovered in the late 1800s, and then kind of really emphasized by Einstein in 1905, was that the speed of light is constant. Wherever you are, however fast you're moving, it always seems that the speed of light is the same. In order to make that work out, Einstein had to invent this idea of relativity and had to kind of say, well, the reason the speed of light seems to be constant is because our way of measuring distance and our way of measuring time changes when we're going at different speeds. That's kind of the origin of special relativity. But in any case, so it's a little bit trickier how the Doppler effect works with light than with sound, but it's the same basic idea. Things that are moving away from you, the frequency of things like light will be reduced. Things that come towards you, the frequency will be will be made higher. So that means light, that when we see light, the red light has lower frequency, blue light has higher frequency, green light is in the middle. That's sort of the way that rainbows work. They're bending should be bending the red light more in the raindrops than the blue light. And but in any case, if you take something that was, let's say, green, and it is moving away from you, it's producing green light, but it's moving away from you, then it will get shifted towards red. And so what one says is that there's a red shift in the light that's being received. Same thing happens with galaxies. A galaxy that's moving away from us is red. The light that comes from it is red shifted, so it goes to lower frequency, and we can measure how fast the galaxy is moving away from us by how much redshift there is in the light that comes to us. And that's we pretty accurately know what the original frequency of the light was, because when atoms produce light, they will often produce light based on changes of the energy of electrons, and the way those electron energy levels, the changes in the electron energy are the same for any atom anywhere. Doesn't matter what the atom that existed 5 billion years ago, the atom that exists today, it will have the same energy of light, the same frequency of light that it produces. So if you see something which should have been light from, I don't know, something from some sodium atom or something like this, and you know it's light from the sodium atom because of its frequency, but you see that it has been systematically shifted to lower frequencies, then that is kind of tells you that sodium atom that produced that light is moving away from you, and you can measure how fast it's moving away. And that's kind of the second big approach is for things that are far away from us, is to measure their redshift. It's usually denoted Z. So redshift of like 1.5 means that the frequency of the light is 1.5 times lower than it would be if it was right here, not moving away from us. So there, as we observe galaxies further and further away, we'll see, redshift 2, redshift 3, and so on. And those correspond to galaxies that we know are further away, because we can work out, based on the expansion of the universe, how far away they should be. Now, there are many tricky aspects to this whole story about the way the universe expands and the way these calculations are done and so on. And there's a lot of kind of hacky stuff that people have tried to introduce to sort of explain why the expansion rate isn't what you think, and the brightness of galaxies isn't what you think. And this has led to the introduction of this idea of dark energy, which I'm deeply skeptical about, which is something that is kind of negative mass matter that kind of pushes the universe to expand faster because it has a repulsive force of gravity. I'm pretty skeptical that that's really going to end up being a real thing, but we'll see. So that's a little bit on measuring distances of things in the universe. Let's see. Let's see. My gosh, so many questions about so many different things. All right, let's do another one that's Igor asks, can you tell us about the science of gem cutting, brilliance, internal reflection, etc.? Let's see what I can do there. So the several different things to say. So light, if it's going through a vacuum, goes at the speed of light. Unsurprising. It wouldn't be called the speed of light if that wasn't the speed that light went at. But when light goes through a material like glass or water or diamond, for that matter, it goes slower. What's happening when light goes through something like water or glass? What's happening is the photons that are the particles of light, they're not just going straight through as they do in a vacuum. Well, actually, even whether they go straight through in a vacuum is a complicated story. That's somewhat our our physics project kind of suggests some slight footnotes to that story. But let's talk about sort of what's in traditional physics. When light goes through something like glass or water, those photons are not just going straight through. They keep on getting absorbed by atoms and then re-emitted by the atom. And there's a tiny delay. After a photon is absorbed by one atom, there's a tiny delay before that atom will re-emit the photon. And that tiny delay causes the speed that the light is moving through the material to be slower than it will be in a vacuum, because you keep on having to wait for the light to get re-emitted from atoms that it was absorbed in. So for example, in water, light goes about 1.33 times slower than it does in a vacuum. In glass, it's maybe about 1.5 times slower. In diamond, it's 2.7 times slower. In diamond, because of the way that a diamond crystal works, it is, even though it's transparent, every photon that comes in actually does get transmitted through the diamond. It is still, there's a delay before those photons are re-emitted every time they're absorbed inside the diamond. Now, of course, other materials that aren't transparent, the photon gets absorbed by an atom and it isn't re-emitted, just it's stuck. The light never comes out. But in a material like diamond or water or glass, at least photons of visible light have the feature that they're absorbed by those atoms, but they are a short time later re-emitted. Okay, so that phenomenon of light being slower in materials than it is in the vacuum is described by the so-called refractive index. The amount that the light is going slower than it does in a vacuum is the refractive index of the material. So for example, water has a refractive index of 1.33, diamond 2.7. Okay, so what consequence does it have that light goes slower in something like water or glass than it does in the vacuum or in air? In air, light goes only just a tiny, tiny bit slower than it does in a vacuum. It just doesn't get absorbed very much by the air molecules. It's a very small effect. There's a very small delay. The refractive index is incredibly close to 1, meaning the same as the speed of light in a vacuum. So what happens as a result of light going more slowly, let's say in water? Well, here's a way to think about it. We can think about light not in terms of photons, little particles of light, but in terms of a whole collection of photons that form effectively these waves that come in, and there's a kind of the wave kind of goes up and down and up and down. It's not quite really going up and down. It's really that the light is made from this oscillations in the electric field and magnetic field, and you're seeing in the different sort of waves in light correspond to electric field being big in some direction, magnetic field being big in some direction, and so on. And that happens for visible light, it happens like 1 trillion times a second that you'll get these oscillations in the electric and magnetic field. But the sort of big picture is that you can think of light as being a sort of wave, of electromagnetic wave that's moving through space or through a material. Okay, so this electromagnetic wave, it's got wave fronts, it's got, the wave is up, the wave is down, et cetera, et cetera, et cetera. And those wave fronts are incredibly close together. They're some number of billionths of a meter apart. They're coming to you at the speed of light, and they're coming, there's a new sort of peak of the wave 1 trillion times a second. Okay, but they're all sort of coming towards, let's say, surface of water. Okay, they're going to go slower in the water. And so what's going to happen is these waves are all coming in, and as they go into the water, they slow down and they kind of bunch up. Well, if you work out the geometry, if the waves are coming in at an angle, they don't hit the water kind of just straight on, but they hit the water at an angle. What will happen is as the waves bunch up, they kind of have to become more vertical. If they were at a certain angle coming in, when they go into the water, the waves become sort of more vertical. So if you look at, for example, if you shine a laser at an angle, glass or water or something, you'll see that it will bend as it goes into the glass or water. And the amount of bending is determined by the refractive index of the material. It's a little piece of trigonometry. It depends on the sines of angles. It's a thing called Snell's law that tells you how much the angle is changed as you go into a material of a certain refractive index. So the thing is coming in, it's at an angle, it becomes more vertical. In an extreme case, it might come in almost grazing the surface of your glass or water or whatever, and then it becomes, well, not quite, it's going into, it's then at a certain angle. Now the question is, well, what happens if you run it the other way around? If you have light that originates inside the piece of glass, and then it's coming out of the piece of glass, then it has to be the opposite. Instead of the angle decreasing when it goes into the glass, as it comes out of the glass, the angle has to increase. And so a tricky thing happens, which is that there comes a point where the angle in the glass is large enough that there just isn't a corresponding angle. The light would be, at some angle, the light, when it comes out, would be just grazing the surface of the glass. But if you make the angle inside the glass even larger, then what's the light going to do? Well, the answer is you get so-called total internal reflection. The light just doesn't come out of the glass. It's reflected back inside the glass. And so above some critical angle, when the thing is too close to kind of grazing the surface of the glass as it comes out, the light will just be reflected back into the glass. Same thing happens with water. If you look up at water at a certain angle, when you look up towards the water, it will just look like a mirror. It's just reflecting the light. So from inside the water, that's what it looks like. If you're a fish or swimming underwater, I'm very bad at opening my eyes when swimming underwater, so I'm not a good one for seeing this effect, but fish will see this effect. That it will just seem like a mirror because the light is being reflected from the surface of the water when it's coming at that angle. Okay, what's the point of all of this? That means that light inside a material, like glass, for example, there's a certain angle at which it will stay inside the glass. In, for example, a rainbow, it's important that light is totally internally reflected inside the raindrop, twice actually for an ordinary rainbow. And no, actually, sorry, one reflection, two refractions, which is the light coming into or going out of the water drop. So you get sort of secondary rainbows, secondary bows, when there are more reflections inside the raindrop. Okay, what is this all relevant to? Well, when you have a diamond has a refractive index of 2.7, much higher than water or glass. And so this whole business of total internal reflection happens a lot more for diamond, and the angle at which it happens there's a much wider range of angles for which it happens for diamond. So a piece of light that's inside diamond will have a great habit of just sort of bouncing around, because if it hits at an angle, at a sufficiently sort of grazing angle, it will just be reflected inside the diamond. Okay, well, so that means if you can arrange the surface of the diamond to be such that when light comes in, it just keeps on, the diamond has been cut in such a way that it just keeps on bouncing. The light just keeps on bouncing around the diamond. The diamond will have this nice kind of sparkling to it, because the light, instead of it being a typical thing that you see, where whatever light you are getting from the material, the object you're looking at, it just comes to you from one place in the object. But in a diamond, when the light has gone in, the light can be bouncing around, and it will come out at you at the light will come out, the light that came in at some quite different angle will come out at you, and it will seem to sparkle, because it's not as if it's not a uniform thing. It's a thing where light from lots of different angles ends up being emitted from the diamond at an angle where it goes to your eye. So the tricky thing there is, can you arrange the geometry of the diamond to be such that there will be total internal reflection? There'll be many total internal reflections inside the diamond. And this is something I think was discovered in the 1600s, I think, in the Netherlands, these so-called brilliant cuts of diamonds, which have the feature that they successfully keep the light inside the diamond for sort of as long as possible to give it as much sparkle as possible. Now, it is not such an easy thing to cut a diamond. Diamonds are crystals, and in a crystal, you have a bunch of atoms. In the case of diamond, it's carbon atoms, and they're all arranged in a very regular way. And so same thing with salt. At least you can have a salt crystal. Sometimes it'll be a perfect crystal. Salt crystals are cubic. Diamond crystals are, oh my gosh, what is their outer shape? I think it is it's one of there are a certain set of shapes that you get from the way that the atoms are arranged inside. The actual outer surface may not, it is constrained by the way the atoms are arranged inside, but it's not necessarily determined by it. Just like in a snowflake, for example, the atoms are arranged inside in a hexagonal grid, but the outer boundary of a snowflake can be kind of tree-like and fluffy because if you looked inside every arm, all the atoms are arranged, all the molecules of water are arranged in this hexagonal array, but which atoms you pick from the hexagonal array is different, and so you can get this kind of fluffy snowflake coming out. But in any case, the issue is, if you've got a crystal and you've got all these atoms lined up in this regular array, that's what a crystal is. A perfect crystal, all the atoms are arranged in this very regular array. Often things are polycrystalline, so they have lots of little tiny crystals all sort of stuck together. But in the case of a diamond, the kind that people really like, the kind that those diamonds are perfect crystals, are single crystals. When you mine diamond, there'll often be lots of little diamond crystals all stuck together, and you'll be looking for what's the biggest perfect crystal in that clump of diamond crystals. And then you pick that out, and then you have to cut that crystal to have the right shape. How do you cut it? What's tricky about cutting a crystal is that if you kind of start, there are ways you can cut a crystal where it's fairly easy to cut, and there are ways where it's super difficult to cut. The so-called cleavage planes, which are essentially places where roughly the knife goes in between the atoms. In other words, let's say you have an array of atoms and they're just all lined up in kind of, let's say, a cubic array, for example, where they're just all lined up in a sort of rectangular kind of pattern. Well, if you try and cut straight down in that rectangular pattern, it cuts quite easily because your knife in effect isn't going through an atom. If you don't go sort of straight down, you go at some funny angle, your knife will keep on sort of hitting atoms. It won't be able to break the atoms apart. It'll have to sort of go around the atoms, and it'll be much harder to cut. So this is sort of the tricky thing, is can you find a way to cut diamond in its kind of cleavage planes in such a way that you can also arrange to have the light be totally internally reflected a lot. And that's kind of the art of cutting diamonds appropriately. And that's what leads to the sort of the brilliance, the sparkle, is this thing of total internal reflection happening many times inside the cut diamond. All right, let's see. Brianna asks, does that mean that objects with higher refractive indices heat up more? Let me think about that. So, no, let me think. I don't think so. Here's what's happening. The higher the refractive index, the longer the delay before a photon is re-emitted from an atom. But it still gets re-emitted. And the energy that comes in from that photon, each photon has a little packet of energy. That's sort of, in a sense, what the photon is. And it is then absorbed by an atom, which means it's taking one of the electrons in the atom and it's giving it more energy. And then after a little while, the electron is like, I'm fed up with having more energy, and it jumps back down to having less energy. And as it does that, it emits the photon again. And it takes it, whatever it is, a trillionth of a second or something, less than that even, to a million trillionth of a second or something, to go from absorb and then re-emit. But no energy is going anywhere else. So when you heat something up, what's happening is that there's energy that's not just getting re-emitted. There's energy that's kind of staying in these atoms, and that means the atoms end up, that causes the atoms to start moving around, to start having kinetic energy, energy of motion. The energy associated with kind of the absorption of a photon is, if the thing is re-emitted again, as it is in a transparent material, that's an important thing. If the material is transparent, the energy that came in with the photon goes out with the photon as well. If the material isn't transparent, then yes, it's absolutely true that that the photon comes in, it's absorbed by the atom stays with that higher energy. And what does the atom do? Well, maybe it'll use that energy to start moving around, and that motion of the atom will come out, correspond to heat. Now, a tricky math fact is the refractive index is telling you how much slower effectively light goes in the material than in a vacuum. When light is absorbed, you can actually represent that by saying that the refractive index is not an ordinary real number like 1.3 or something, but it's a complex number that's like 1.3 minus 0.2 times I, where I is the square root of -1. It turns out that that's a way of describing the absorption as well as the change in speed of that light wave. And the reason, okay, math moment here, a light wave you can represent by a complex exponential like e to the ikx, for example, and well, let's see, this is going to get too complicated. But basically, the speed of light shows up in that complex exponential, and if the speed, including the refractive index, shows up, if the refractive index has an imaginary part, that e to the I times something turns into the e to the minus something, and that means that you're representing not that you keep on just having the same magnitude, but you have a decaying magnitude. Okay, that was a bit more mathy than I usually end up getting in these live streams. Maybe it'd be fun sometime to do one of these where I'm allowed to get mathy, but if it's re-emitted, the energy doesn't stay in the material, so it doesn't heat up. Let's see. Okay, Bernard, so there are materials that slow light down enough that we can actually see it traveling without technology helping us out. Yes, there are some materials that I saw them once in a lab. There are materials that manage to slow light down so much that it's traveling at kind of speeds you can see. They're very weird materials. They're materials that involve atoms that have kind of all collected in exactly the same state. Roughly what happens is, in a laser, the way a laser works is photons, if they're given the opportunity, all like to act exactly the same. They like to have the same frequency, going in the same direction, etc. Lasers kind of arrange for that. And that's kind of why the laser light is sort of all going in one direction, etc. You can do the same kind of thing with atoms. You can make so-called Bose-Einstein condensates, which are kind of the analog for atoms of lasers for photons. They're something where the atoms, certain kinds of atoms, can be set up so that they sort of all like to be doing exactly the same thing. Those kinds of materials can be used to make sort of ultra high refractive index effectively materials. It's kind of not a material like a thing you can pick up and wave around. It's a pretty tricky thing that involves these atoms caught in these sort of traps and held somewhere, and it's not a solid object that you can pick up. It's something more abstract than that, at least the way those things have been built so far. Let's see. Okay, other questions here. Let's see. Some of these are long. Okay, Jerome asks, how would you describe science? And how are you staying a scientist? How would I describe science? What is science? Well, I think a way to describe science, and let me preface this by saying that there are a certain set of studies that have traditionally been called science. Science got such a cool reputation that a lot of things that aren't science in the same way that science originally was attach the word science to what they're doing. So there are things that are called sciences that are not really science in the way that science was originally imagined. How was science originally imagined? It was originally imagined as a way to kind of talk formally about the world, as a way that we see in nature all kinds of things happening. The question is, can we produce a kind of human explanation of what's happening in nature? We see things, I don't know, planets moving around. We see, I don't know, waterfalls falling, and we see this and that and the other, rainbows happening, all these kinds of things. We see these things happening in nature. The question is, can we produce kind of a human description of what's going on? Can we tell a story about why does a rainbow happen, as opposed to just saying there's a rainbow? Can we sort of take apart how rainbows work and talk about a mechanism for rainbows and so on? And sort of the essence of science, I think, as science was sort of originally conceived, was how do we explain the world? How do we talk about the mechanisms of things? And so science was developed particularly in areas like physics, where there was a lot of success in saying, here's a law, it's described by mathematics. Go see the consequences of this law, and that explains what you actually see in nature. That was sort of a key central part of science. Similarly, in something like biology, when you could look through a microscope and see, oh, this thing is made of this and this and this, it's again a story of how it works. What is the mechanism? How does this kind of creature, digest its food or whatever else it is? It's a kind of a story of mechanism. How do things work? And I think that's sort of been the traditional essence of science, is taking what is out there in the world and saying, how do we explain it? How do we describe a mechanism for it? And that's, the physical sciences, the biological sciences, chemical sciences, those are places where that kind of find the mechanism story is a story. Now, then one extends to things like, well, let's say behavioral sciences, cognitive science. Cognitive science maybe is the same sort of thing. Can you find a mechanism by which brains manage to do this or that? Computer science, a little different, because computer science is not really about, here's what happens in the world with computation, now understand the mechanism. It's more about studying kind of what can you do with a computer, so to speak. There is a form of computer science that I tend to call ruleology, which is just asking, pick a program at random, not a program a human wrote, just a program where you set up a set of rules, you just run them and you see what happens. That is more what should be called computer science, although the ship sailed long ago on that. Computer science is what it is. That has to be given a new name. I've called it ruleology, the study of simple rules and what they do. But that's something more like natural science applied to computers. It's like, here's what happens in the computational universe, now understand mechanisms for it. As opposed to traditional computer science, which is much more, how can you build things with computers, which is not really the traditional meaning of science. I think in as I say, it's been a little confusing because many things have attached the name science to themselves because science is thought of as being cool and thought of as being definitive, so to speak. And in a sense, why is science thought of as being definitive? It's because once you kind of know the mechanism, it's kind of like it's always going to happen that way because you know why it happens. It works really well in physics. In physics, there are good, strong laws that let you see, given that law, you can predict lots of things in physics. In biology, for example, you can do that to some extent, but there haven't been kind of sort of underlying strong laws in biology. It's more there's this particular mechanism, this leads to this, there's that particular one leads to that, and so on. It's still a build-up kind of thing where you're talking about mechanisms, and so it sort of follows the science path, but it's not as strong, it's not building as big a tower from sort of the foundations of what's happening up to kind of what you actually observe in the world. I mean, my own efforts in both physics and recently in biology have been all about kind of how do you make it as sciencey as possible in some sense, in the sense of going from as low level of foundation, as simple a set of primitives as you can, to building up to as elaborate a description of how the world actually works as one can. Now, another thing that sort of came with the science package, at least in physics, starting in the late 1600s, was the idea that science allows you to predict things. It allows you to say, given that I know this and this, I can predict this is how this and this will happen. That's been more true in physics, the physical sciences, than it's been true anywhere else. If you say in biology, can you predict sort of in the abstract what will happen in, let's say, the course of biological evolution over the next 1,000,000 years, what will happen? We really can't say that much about that, or haven't been able to. I think some things I've done recently give one a little bit of more of a theory of that. But in any case, the thing that sort of got part of the science package ended up being, and we can predict. And that became, in the 1950s particularly, people started to say kind of the test of whether it's really science is whether you can make predictions and then you can verify them. You can see, did the prediction work out? Could you falsify the prediction by showing, oh, it didn't work out the way you expected, so the theory you have underneath must be wrong. That approach became very sort of popular in science. It doesn't quite work as well as you might think. And the reason is there's this phenomenon that I've studied for a long time that I call computational irreducibility. And the issue is, if you have a theory about how something works, you know the underlying rules that the system is going to operate according to, it's not obvious you can say, oh, then I know everything about what the system does. Because it could be the case that you just have to run those rules. You just have to keep running them once, twice, 1,000,000 times, 1,000,000,000 times. And the only way you can know what the system is going to do is just to run every step in the rules for, let's say, 1,000,000,000 steps to see what happens. And what I found is that there are an awful lot of systems that one can invent on a computer and that one can observe in the world, in the natural world, which do have this phenomenon of computational irreducibility. You can't know what's going to happen other than by just following each step and seeing what happens. And so kind of one of the traditional kind of feathers in the cap of it's made into a science that you will be able to then jump ahead and predict doesn't really work nearly as broadly as people might think. And it's sort of a fundamental limitation on science. Now, people get misled because they say we've turned it into a science. We know its mechanisms, so therefore we know everything about it. It's not true. It can still be the case, even though you know the underlying mechanism, to know what will actually happen on a large scale, you may not be able to work that out. You may have to just follow the steps and see what happens. Sometimes you might be able to jump ahead a little bit with a computer, but if you're dealing with, what's going to happen to sort of all the molecules of gas in a room or all of the water particles in the atmosphere or something, that's much bigger than we can simulate on a computer. And insofar as there's computational irreducibility, the actual computation happening in the system itself is far out of reach of what we can kind of simulate on a computer and jump ahead of. So in a sense, that's a confusing aspect of science. is that from within science comes this phenomenon of computational irreducibility, which tells one that one of the things that one thought was an important feature of science, that is, being able to make these predictions, isn't really something that comes along with the bundle, along with kind of the idea of understanding of mechanisms and so on. So I think the second part of this question was, how are you staying a scientist? I'm not quite sure what that means, but the thing, in science, there have tended to be several different overall approaches to science. There's doing experiments. There's making theories. The sort of theory and experiment are two traditional branches of ways of doing science. When you do experiments, you set something up, you have to make it, if possible, so that you know exactly what you're putting into the experiment. I'm mixing these chemicals together in this concentration at this temperature, in this way, I'm stirring them in this fashion, and in the end, they're going to turn green and do whatever they do. But you're sort of precisely setting things up, and then you say, okay, universe, just run with what I set up, and what do you get out? And then you have to look at what comes out. You have to say, well, let me measure what came out and make a conclusion from that. So doing experiments is one sort of branch of how to approach science, is just set things up very carefully, see what the world does with what you set up, then measure what comes out. That's, and in most sciences, there is an experimental component. The other approach is theory. Say, okay, I think I know the underlying laws, or maybe I can come up with underlying laws. They're abstract laws. They're represented computationally. They're represented mathematically, whatever else. Then I take those laws as a theory, and I work out the consequences of those laws, what those laws imply for what should happen in the world. Those have been two traditional approaches. Kind of computation is something a little bit in between those. You can do an experiment on a computer. You can say, I'm going to set up this law, this theory, this rule on a computer. Then I can just run it on the computer and see what happens. I've been doing that for, oh gosh, nearly half a century now. And I've discovered lots of really interesting science by that approach of doing what is, in a sense, an experiment, but it's not an experiment with physical kinds of things. It's an experiment with just abstract things in a computer. It's a lot easier, actually, I think. Because it's not like if you do a chemistry experiment or something, you have to make sure the test tube is clean and all that kind of thing. If you do an experiment with animals or something, you have to make sure your mouse is well fed that day when it does the maze or whatever. If you do experiments with people, there's even more of a can of worms. Even physics experiments, a little bit cleaner, but still a lot of detailed things about, there's a little bit of extra light that crept into my apparatus, let me put some more, black tape on this thing. There's a lot of tricky things that you have to do to get an experiment to actually work right. And, one of the things that's a big test for experiments is, can you reproduce the experiment? If you take the description of the experiment, can you run it again and get the same answer? And in many areas, that's been incredibly difficult. Particularly in the biological sciences, it tends to be very difficult to get reproducible experiments. And in behavioral science, for example, where it's, do the people do this or that thing? It's almost, it's sort of a disaster in whether you can, whether there's, people talk about sort of a reproducibility crisis of the fact that so many things in behavioral science and medical science, things like that, you do the experiment again with the description that you had, and it just doesn't come out the same way. Computer experiments are nice in that respect, because if you set the computer up to do the same thing, it will do the same thing every time. And there's a certain art to doing computer experiments well, but similar to the art of doing physical experiments well, you kind of have to set up a very clean, simple experiment. So when you get some result from the experiment, you can interpret it. You're not saying, I don't know why it did that. It must be one of the 1,000 things that I put into this experiment. One of those had the effect that produced this effect. You want to have a very simple experiment where you can see everything you put in, and then you can kind of, there's nothing hidden that you put in that you didn't have coming out. I mean, it's like, it reminds one of kind of the the famous story of a sort of, you could think of it as an animal behavior experiment, this horse that people thought could do arithmetic. And, you'd ask it some arithmetic and it would, move its foot, that number of times to correspond to that answer. But it actually turned out that the trainer of the horse was perhaps unconsciously kind of giving the horse a clue about what the number should come out to be. So that's a case where sort of there was extra stuff in the experiment that you said, well, it's just a horse, it's there, and somebody's holding the horse. But actually the person who was holding the horse was unwittingly giving extra information to the horse. The experiment wasn't a clean experiment. And that's, with computer experiments, a lot easier to have them be clean experiments. But in any case, in different fields of science, there are different levels of enthusiasm about experiment versus theory and so on. In physics, for example, experiment and theory are kind of neck and neck. A lot of experiments are done, a lot of theory is done. People expect that the theory will predict experiments, the experiments will inform the theory and so on. In something like the biological sciences, people mostly think it's all experiment, no theory. If you're doing some study, some medical test study or something like this, people say, well, just do that clinical trial and just measure it. Just see, you have 100 people in the trial, 73 of them do better and 4 of them do worse and so on. You just measure it. If you say, well, there's a mechanism, there's a theory for what's happening, people are like, we don't really care. Just measure it and see what happens. There's not really a belief that theory works in the case of biology and medicine. Actually, some recent things I've done kind of suggest how one can have a theory to some extent in biology, and actually also in medicine. I happen to be working on that right now, of trying to understand to what extent you could imagine having a formalized theory of medicine in the same way as you have a formalized theory of physics. You can't get nearly as far as with physics. Computational irreducibility kind of bites you quite quickly, but it's interesting to see how far you can get and to what extent things which are just, oh, that's a thing everybody knows about medicine, but there isn't really a theory to it, to what extent you can inject theory into that. But so different fields have different sort of amounts of theory versus experiment. And physics is one of the most successful areas in terms of theory. Now, there are other fields that perhaps aren't really sciences. I mean, computer science, as I say, there aren't really experiments in the same sense, except in these areas like rheology and so on. In mathematics, insofar as it's a science, and I'm not sure you really should call it a science as such, there are mathematical sciences which use mathematics to make their theories, but mathematics itself doesn't really have this character, or doesn't at first seem to have the character of ordinary science, where you're sort of thrown something by nature and then you have to kind of explain its mechanism. Mathematics is a bit different because it's more like you've given this formal thing and you have to see the consequences of that formal thing. You know the rules for making up geometry or something. Now let's work out what actually are the consequences of those rules for geometry. Now, I actually think that mathematics can be pursued more like ordinary science, that it is like there are laws of physics that lead to all kinds of phenomena. And in our physics project, we think we've sort of figured out what the lowest level laws, the fundamental laws, the ultimate machine code of the universe is like. And insofar as we've managed to do that, everything else is kind of like mathematics. One is building up from this underlying formal structure, this set of rules one knows, so to speak, or at least one knows the general form of those rules. And then everything about how physics works is something that in principle one could work out from those rules. Just like in mathematics, everything one's going to figure out, one in principle can work out from the underlying rules about how numbers work and things like this. So that's kind of particularly, well, in mathematics, people have tended to view it as being really a theoretical kind of thing. You're working things out formally, you're proving theorems, you're doing things where you are sort of, it's all kind of all mechanism, all explanation, all the way down. I don't think that's actually quite right. I think that mathematics really should have an experimental branch where you say, well, there are these underlying rules in mathematics. Now just work out on a computer, what are the consequences of those rules? I've done a fair amount of that. Experimental mathematics, where you're just saying, these are the rules for numbers. Now what consequences do they have? Well, they have maybe some very weird consequences where we can't yet give a narrative explanation for why it works that way. You have some thing involving primes and you notice some particular pattern and so on. It's like, well, why does it work that way? It's then a question very much like ordinary natural science, where you have to kind of drill down and say, I know what happens, now why does it happen? That hasn't been the traditional view in mathematics. In mathematics, more it has been, let's build it up. Let's see how we can build up what must happen, rather than sort of observing experimentally what does happen. So I would say that in the sort of definition of science and theory and experiment and so on, mathematics, there is an experimental mathematics that is more like traditional science that hasn't been pursued as much as it absolutely should be. Anyway, a few thoughts about the nature of science. Let's see. Things about science here, let's say. Let's see. There's a question here from Atori. Can I talk about scientific paradigms? What people tend to mean by a scientific paradigm is kind of a way of thinking about how the world works. For example, one paradigm might be using mathematics to think about how the world works. Another might be using computation and programs to think about how the world works. Another might be something about, in biology, something about knowing that that sort of molecular things are what determine how things work in biology. Scientific paradigms tend to be about sort of the way of thinking about things. I don't know, something like natural selection and the theory of evolution. It's before that, it was kind of like, well, there are all these species and they just happen to be the way they are, as opposed to a sort of a paradigm where we can imagine an origin of species. We can imagine kind of a narrative that we can tell about why the species work the way they do and how they're produced. So what tends to happen is paradigms are ways that one thinks about things. And once you've learnt one, that's a big investment to learn it. And that then becomes the way you think about things. And when somebody says, well, there's this different paradigm, it's often very hard to adjust to that different paradigm. And, I've seen that in my own life. Was fortunate enough to kind of get involved with thinking about things in terms of computation a very long time ago, more than 50 years ago now. And that paradigm has turned out to be pretty fruitful. Lots of things can be figured out with that paradigm, but I can kind of see that people who haven't really kind of gotten deep into that paradigm, they just don't get it. And there are surely paradigms out there that I just don't get. Every field has certain paradigms in which it operates. A field that I've been planning to learn is economics, which has a bunch of paradigms for thinking about sort of how things work that I don't think I understand yet. I don't think I can reason in the way that economists reason yet. In mathematics, there is sort of a paradigm of theorems and proofs and so on. That's a way of thinking about things. And paradigms are perhaps one of the more difficult things to kind of, it's not just a question of learning facts to learn a new paradigm. You have to learn a bunch of facts to kind of fuel your ability to learn a different way of thinking about things. But it's tricky. And there tends to be this phenomenon of sort of paradigm shifts in the history of science, where a lot of people are in one paradigm thinking in a particular way, and then, well, actually, to make progress, you need to pick a different paradigm and think a different way. And it's a very difficult thing for a community of people to kind of shift and go in that other direction. And often what happens is that it's a new field that gets developed that's using a new paradigm, and the existing field kind of just goes the same way as it was going before and doesn't capture whatever new direction there is. So this happened, for example, in probably the 1940s and 1950s with mathematics and computer science. Computer science was off with people writing programs and things like this. It kind of came out of mathematics, but mathematics, people are like, we're not writing programs, we're making proofs of mathematical theorems. It's a different paradigm, it's a different kind of thing. Let's see. A comment from the Frey. It's an interesting parallel talking about reproducibility, parallel to current research in LLMs that have so many variables, so much variability, that reproducibility is extremely hard, even if it's just computers. Yes, that's absolutely true. It's a very, we've built a lot of LLM-based functionality for Wolfram language, like our recent Wolfram Notebook Assistant. And it's a frustrating thing because you can't even demo it. It's kind of like I've been used to doing computer demos for 50 years, and I'm used to, I type something in, it's going to give the same thing it gave the last time I typed it in, or at least if I'm using the same version of a program or something. But with an LLM, all bets are off. You type something in, it's going to go off. Typically, the way LLMs are run, they have a certain randomness in what they produce. You can run them without that randomness, but they tend to do things that are a little bit flat. But that means that there's really no predictability. Even when you run them without randomness, the way that LLMs are actually implemented on GPUs and things, you get a certain tiny amount of randomness because of really subtle effects that have to do with the fact that the way that GPUs process, the way they're set up to run as fast as possible, they do things like predict what the next instruction that you might feed in might be. And they're rearranging how they do instructions based on what they think is coming in. And those rearrangements can have very tiny effects on numbers that come out. But those rearrangements, how that happens depends on a lot of things about what's going on in your computer in general. So there's kind of an injection of randomness, even when you think it's just working out a bunch of things with numbers. What's happening is those numbers, you have 3.7258446, whatever, bunch of digits. After you go about 16 digits on a typical computer, that's as many digits as the computer is storing. But there's sort of a question of what happens to that last digit that isn't quite what the computer is dealing with, the round off error of the last digit. And depending on exactly how the arithmetic was organized by the GPU, you might get a different answer. It's a very tricky effect. It surprised me a lot a couple of years ago when LLMs were first out and about in the world, that even at zero temperature, zero obvious randomness for the LLM, there was still randomness. And I finally tracked it down. It took me going to talk to some hardware designers I know to actually find out what was going on. But it has to do with these, it has to do with some pretty subtle effects. I mean, to be a little bit mathy again, in ordinary arithmetic, it's the case that A plus B plus C gives the same answer as A plus B plus C. Doesn't matter where you put the parentheses, you'll always get the same answer. Well, it turns out that's not true in computer arithmetic. When you're only keeping a limited number of digits in your numbers, it turns out that associativity phenomenon doesn't work anymore. So the mathy thing where those are equal, which they are if you're dealing with exact numbers, isn't true on computers. And that's one source of randomness, even in the case where you think there's no randomness. But yes, the fundamental point is doing experiments on LLMs and so on. It is, again, a story where it's like doing experiments, not that I've ever done experiments on rats and mice and so on, but at least my imagination of what's involved there is, you try and coax the mouse to do the rat, to do the maze the way you want, and well, it doesn't. It loses interest. It goes off and eats a piece of cheese instead. And I feel that LLMs, doing experiments with LLMs, a bit the same kind of way. The way I've often described it is, the LLM is kind of like a wild animal. And particularly if you're like doing a public demo of an LLM, it's like you've got a wild animal on stage with you. And if you're lucky, you can kind of keep it, you can wrangle it well enough that it will more or less do the trick you want it to do. But you can't be sure of that. And yes, it's a tricky thing. And it is interesting. And I don't really know Yeah, I don't really know how to think about that. I mean, it's much more similar to doing psychology experiments, which are notoriously difficult to reproduce. Doing experiments on LLMs is much more like that. I mean, there are some experiments you can do in psychophysics, with optical illusions and with, flashing lights quickly and things like that, where it is very reproducible. But when it comes to, what's the preference of somebody when they're shown this and shown that, and so on, that becomes often very difficult to reproduce. Let's see. Let's see. Chatty is asking, do you think science has a problem with trying to tell nature how to behave rather than reporting on what nature is telling us? Well, in a sense, engineering and technology are the attempt to make the world do something that's useful to us using the raw material that's in the world. And I think in kind of that's really the way that we get to that. That's the writing to nature form of science is technology. The reading from nature is the science. I think it gets tricky in the actual doing of science. Science, to do science well, involves it's in some sense it's a psychologically difficult thing because you have to have enough of a hypothesis, enough of a guess about how things will work that you try the right experiment or study the right theory. But you have to be not so committed to the thing that you think might be true that even when the chips fall in a different way, even when nature shows you something different, that you then keep chasing it, even though it's not actually what nature is telling you. And that's sort of a trap in doing science. If you just say, I know nothing, I'm just going to look at nature and try and guess what might be going on, that's also not terribly productive. You have to be like, I've got a hypothesis. I'm going to look at this aspect of nature. I'm going to do this thing, I'm going to do this kind of experiment. But then you've got to have some hypothesis, but you've got to not be so wedded to your hypothesis that even when nature shows you that that hypothesis is not really correct, that you keep on trying to twiddle it so that you get it to be correct. And this is where, in some areas of science, there have been really disasters because people, and particularly true, I think, in sort of behavioral science and psychology and so on, that people will do these experiments and they kind of have, I know what's going to happen. I'm sure it's going to be this way. And then it comes out a certain way and it's like, well, the reason that happened is because this group of people who I tried to give this questionnaire to, they were sick that day. And these other set of people, well, they just read something in the newspaper and so they were off kilter. And so I'm going to ignore those parts of my study, even though, and then I'm going to get the effect that I thought was there. It's very easy to kind of fall into getting the answer you thought you were going to get just because you make up for yourself reasons why the things that would take away from that answer aren't what should be part of the experiment. It's difficult to do science in such a way that you are kind of, removed enough that you can just let the chips fall as they fall. I think for myself, I've done science long enough, and particularly with computer experiments, there is a very humbling aspect to computer experiments, which is you set up these rules, you have a guess about what's going to happen, and so often what actually happens is something you could never guess. But it's right there. You can't get out of it. It's no kind of, oh, well, maybe, the computer wasn't feeling well that day. No, it is the way it is. And it's the way I usually describe it rather whimsically is the computational animals are always smarter than we are. When you run these computational rules, they do things that you never imagined. And you kind of have to, that's where the chips fell, and that's what you have to kind of live with. Let's see. Spare Parts is asking, when you're demoing something with LLMs, what if you start the prompt to the LLM with a script for the tech demo and ask the LLM not to go off script? I have not tried that. My guess is it will not work perfectly. I mean, I think there is sort of this emerging field of LLM psychology of kind of knowing what are they going to do. I mean, I feel like I'm getting some feeling for what LLMs, for how LLMs react to things and so on. I know people at my company who do a lot more LLM prompting, LLM engineering than I do, probably have a better intuition for this. I feel like I'm not quite up that curve, but there are definitely things feelings you can get, and it's kind of like, what is the psychology of the LLMs? What, if you push them really hard, what are they going to do? Are they going to push back? Are they going to do what you want? What's going to happen? Are they going to, can you trick them in this way and that way? Can you, these are things, if early in the prompt you said something terrible, does that give the LLM a trauma that will, show up later on and so on? I don't really know the answers to these things, but I think some people have gotten some intuition about that. Is there going to be a theory of those things? Is there going to be a science of those things? I don't know. I think it's similar to the sort of science of psychology, which is a challenging thing to have a kind of solid narrative science about. Let's see. Lolly is commenting, I'm often amazed at how LLMs sometimes reproduce realistic human behavior. We've seen them lie or try to cover a mistake. Yes, but you know what? That's because they learned from the humans. I mean, they've, gradually, they haven't yet watched all the movies, but they will. It's like they're doing what the humans do. That is what an LLM is set up to try and, in the case of language, to try and sort of continue the sentence in a way that is sort of typical of the way they have been trained to continue based on training that comes from the way humans have continued sentences, a trillion words on the web or something of the way that humans have written things. And so it's not surprising that they behave in human ways because they learned from us, so to speak. And insofar as, people say, well, we want the LLMs to always do the right thing, always do good or whatever else. The problem is and then people say, well, how do you define that? And then they say, well, sometimes they'll say, well, just make them do what the humans do. And then humans will say, but look, humans lie, humans do terrible things. We should get the LLMs to be different from that. And that's then a very complicated story of philosophy and ethics and sort of things where there isn't really a right answer. All right, I should wrap up soon here, but let's see if there are a couple of questions that I can maybe handle quickly. Let's see. Tori is asking, what's your intuition now for what makes the best prompter? I'm not sure quite what that means. In terms of people, one of the things I noticed from very early in our efforts with LLMs going back to late 2022 is people who are good expository writers are often good prompt producers. If you can explain stuff well to humans, then you can explain stuff well to LLMs. I mean, we found that in the Wolfram Notebook Assistant, a lot of what it's doing is based on kind of what it learnt from documentation we've written about how to use Wolfram language and what people have written about how to use Wolfram language. And insofar as there are places where it's better or worse, where the exposition is better or worse, sort of going in, that is reflected in whether the LLM does a better or worse job of being able to pull those things out. Let's see. Let's see. Well, let's see. Brianna is asking, do you have suggestions on coming up with ways to test hypotheses, especially ones that are more theoretical and difficult to test in the real world? How do you know when you have a good test? I think that's a little bit hard to answer in general. I mean, keep it simple is the most significant thing. I mean, I'll give you an example, bad example, this is 1980s, people studying biological evolution. People were like, it's great, we can make computer programs that do biological evolution kinds of things. Actually, strangely enough, these ideas have very recently come back again in more or less the same way. Say, we can make these computer programs that have all these features. They're imitating a rainforest, and they've got critters on the ground, and they've got critters in the trees, and they've got flying ones, and they've got plants that things eat, and so on. It gets pretty complicated. And then they say, oh, we've, in this whole very complicated thing, we've observed that there's like co-evolution of two species or something, or this is the way some parasite works or whatever else. And it's like, well, really, that's not surprising because you've got all this detail that comes from the actual system. But what's the essential phenomenon that you're observing? You have no idea because it's drowned in all of this detail of all these thousands of parameters and different things and so on. So I think one thing is always try and have everything be as simple as possible. You've got if it's a physical experiment, just keep it kind of as minimal as you can. Don't add in that extra sort of decoration on the wall of the maze for the mouse or whatever. Don't add in that, try and keep it as absolutely minimal as you can. And that's certainly true for computer experiments and so on. I think that's the way that you have sort of the most the most power is where you say, this is the tiny amount that I put in, this is the thing I got out. There's a connection between what I put in and what I got out. If you put a ton of stuff in, you don't know whether that particular feature of what you got out is from some detail that you didn't imagine, like the horse trainer for the horse that counted, or something different. So a few thoughts on that. All right, I think I should really go to my day job, but this is too much fun. Let's see if I can do just one more, he says. Maybe two. We're going back to some physics here. Money is asking, how are diamonds made? Well, in a crystal, what you have to do is get all those atoms to be lined up in this very regular way. And one way that can happen is you're kind of adding one atom at a time, and it's finding where to go based on sort of how it fits into the structure that's already there. There's a huge art to growing perfect crystals. It's particularly been developed for silicon crystals that are important for making microprocessors and other electronic components and so on. There's you heat it up, you cool it down, you do this, you do that, you have a certain rate at which things grow. And that's, in the case of making diamond crystals, it's sort of the same story. Natural diamonds are made in the earth. They're made under high pressure. In order to get the carbon atoms to go into the configuration that makes a diamond crystal, they have to be being pushed with lots of pressure. If that isn't the case, those carbon atoms will form other things like graphite or buckyballs, which are also just made of carbon, and they won't form into that perfect crystalline form. Now, there are artificial diamonds which are made by just putting as much pressure as there might be inside the earth on carbon and forming a crystal that way. And I don't think there's really any difference between a diamond is a diamond. It's just a bunch of carbon atoms arranged in a particular way. Natural diamonds tend to have little extra atoms that crept in there, and they tend to lead to all kinds of fun things of different shades of color and things like this. But in the end, it's like saying, do you have an artificial carbon atom or a natural carbon atom? A carbon atom, every carbon atom is the same as every other carbon atom. Similarly, every crystalline array of carbon atoms is the same as every diamond array, for example, is the same as every other one, except for the fact that there might be some little imperfection that crept in. Okay, one more I noticed here. How was it? Let's see. There was a question about, maybe I'm tempting fate here by trying to answer this one. Chatty asks, or trying to answer it quickly, Chatty asks, can fermions adopt a condensate configuration or not? Okay, let me try this one. So I mentioned before that photons of light like to all sort of get in the same state. And I mentioned that some atoms like to all get in the same state. There are two kinds of particles that exist, so-called fermions, named after Enrico Fermi, and bosons, named after, oh my gosh, what is his first name? Indian physicist named Bose, but I don't remember his first name, which is it's a long name, so I think I get a little bit of I think it begins with an S. In any case, the fermions, things like electrons are fermions, protons are fermions, photons are bosons, and some atoms are some nuclei are bosons, some are fermions. Essentially, the way it works is electrons have a spin of 1/2. Protons have a spin of 1/2. Photons have a spin of 1. Things that have integer spin, whole number spins, are bosons. Things that have half integer spin are fermions. Why that is, that's a thing called the spin statistics connection. I think I've talked about that before. It's a fancy result from quantum field theory. Let me not talk about that. Let's just take it as a given that things with integer spin, whole number spin are bosons. Things with half integer spin are fermions. Okay, so very different. If you kind of try and crowd together bosons, you try and crowd together fermions, very different behavior. In the case of bosons, they all kind of want to be in the same state. They all want to have the same momentum, the same energy, the same everything. Fermions, on the other hand, have a so-called exclusion principle. They always try to avoid being in the same state. So in an atom, for example, you never get two electrons in the exact same state. And in fact, the fact that electrons and protons, things like that, don't all want to be in the same state is why matter is stable at all. That's why kind of you can't crush things infinitely, because they insist on being apart, excluding each other, not being in the same state. If everything was made of photons, you'd just be able to crush it completely. Well, independent of the fact that the photons are going at the speed of light. But actually, there's a little bit more to the stability of matter than that. But in one of the things that contributes to the stability of matter is the exclusion principle with fermions. There's as I said, there's a bit more to it in full detail. But okay, so these bosons, they want to be in the same state. That is why you can make lasers. It's why you can make so-called Bose-Einstein condensates. The fermions want to exclude each other. Turns out there are ways that fermions can still make these kind of be in the same state kind of things, because they can pair themselves up. And that happens in superconductors, where you have essentially electrons in a material where the electrons, which would normally be excluding each other, make little pairs. They're called Cooper pairs, where pairs of electrons, which have like spin a half plus spin a half, make spin 1 or spin 0, depending on whether they're aligned or not. Then those pairs behave like bosons, and they can kind of collect in the same state. Now, normally, when you have fermions, you end up with, they can never be in the same state. You kind of get this whole kind of tower of fermions in different states. They build up kind of to the so-called Fermi level. They build up you have these electrons, and they can never be in the same state. So they have to keep on having a little bit more energy. The next electron you put in has to have a little bit more energy, a little bit more energy. You build up this kind of sea of things like electrons that all have slightly different energies. And in fact, you can make this sort of thing, which the analog of a Bose-Einstein condensate is a kind of degenerate Fermi sea, which is the kind of these electrons all with slightly different energies. So the answer is I think I need to describe this in more detail. Yes, I was living too dangerously here. This is not an answer that I can give in enough fullness in a short time here. So I think this is one of these. Ask it again another time, and I'll try and talk about it in a bit more detail. So better go back to my day job here, but thanks for asking lots of very interesting questions, and I look forward to chatting with you all another time. And yeah, bye for now.